Hello, let's talk about some of the most central objects in analysis and geometry, the notion of curves in a space. To us, a curve will be a continuous map from some compact interval into the Euclidean space. The way we think about them, of course, is the path of an object that is traveling in time. So at time t equal a, you are at some position, and as t evolves, you travel on a trajectory, you end at time t equal b in a probably separate location. Of course, curves in this definition can have self-intersections, they can even overlap along a whole segment, or just it could be a constant curve that doesn't move anywhere. So also, there is an important point to emphasize right here, and that is we define the curve to be a function, not a subset of your Euclidean space. Although we always kind of cheat and imagine the curve to be its image. So the curve, the subset of the Rn that you see in this picture, is the image of the whole interval AB. So this is the image of the curve, and the curve itself is defined under this definition to be a function and not a set. So in calculus, one learns two separate definitions of what a length of curve should be. Of course, there you also add the assumption that your curve is one-to-one, it doesn't have self-intersections, unless probably just the endpoints coming back together and making a loop. And then one of the ways to construct the length is to put along the curve some nodes, and then you get a broken curve of lines that connect the consecutive nodes. So you go along these blue lines, and then you connect the blue lines, and now you will say that the summation of the length of these segments is a good estimate to the parameter of your original curve as you put more and more nodes on it. Of course, this is not a new notion, and it was something done way before calculus was even invented. So let's see what this definition looks like on paper before giving you the other way of computing the length of a curve. So the nodes here you have is a partition of the interval a and b. So you pick a natural number which tells you how many divisions you want, and then you fix points. Your first point should always be your a, the point you start. Then there is t1, and then there is t2, and then so on until in finite time, it's never infinite, you reach tn minus 1, and then tn, which is always to be your last, the end of your interval. Then the blue line segment's length is nothing other than you look at the distance of, well, the length of a straight line is just distance of its endpoints. So this will be ti plus 1. Now we are in the target, minus gamma of ti. This is a vector, and its length is exactly that distance between the 2 points. And then you, of course, do the summation, I going from 0 to n minus 1. You can double check that this actually covers everything. Now, as I said, you have to do more and more nodes, and also look at all possible ways of placing these nodes. So you take a huge supremum over all such summations. So you will take supremum of the quantities you got above. So let's not repeat it and say the gamma, length of gamma is by definition the supremum of all such sums over all choices of n and ti's. So that's a huge collection of possibilities, but thanks to the magics of real numbers, the supremum is always defined. We say a curve is rectifiable, a fancy name for saying it's of finite length, if this length you get is actually finite. Okay, so we saw the intuitive reason behind this definition and also the formal rigorous definition as well. Now, what is the second way of defining, or just the recipe that they give you in calculus for computing the length? Well, here this only applies to more regular curves, and for instance, if gamma is C1, that means it has a derivative and that the derivative is continuous, then this, you take the derivative of gamma, which is a vector, it's the velocity, but then you only look at its norm, which gives you the speed of the curve, and then you integrate it from a to b to give you, so then this quantity is a candidate for the length of a C1 curve. So of course this needs more justification, and if you know a little bit of manifold theory, then definitely you know where it comes from. And for calculus students, we simply tell them this is how you compute the length of a curve. So here gamma prime of t will be a vector, and we only take its norm, and then it becomes a real valued function. The assumption that the function is C1 and not just differentiable tells us that this gamma prime t is actually continuous, and so the integral is well defined. Now ultimately one proves for C1 curves, let's say maps gamma AB into Rn, we have that this previous definition of length that we had actually agrees with this integral. And that's good news, because then we are talking unambiguously about the length of curves in Rn. Now in a separate video, I will prove this result. That these are equal, because the proof is actually quite interesting. But for the rest of this video, what I want to emphasize is a huge difference between these ways of defining the length of curves. Although they ultimately end up to be equal for C1 maps, there is a huge difference between these two. So if you look at the definition via the derivative and length of it, just imagine how much structure has gone into this. Number one, you have curves into a target space that you can talk about their derivative, and that talking about derivative requires linear structures. So Rn definitely has that, so derivatives are well defined. Then you talk about the absolute value of the vectors, so you have a norm on them, at least, if not a dot product, and then only then can you form such an integral and talk about its meaning. However, for the other definition, all you needed to do is you did some partition of the unit interval, the compact interval, So this is something that happens in R and has nothing to do with what target space we map into. And then in the target space, all you need to do, although you subtracted gamma ti minus 1, ti plus 1 from gamma ti, and so these are vectors, so you have to be able to subtract them, but actually we didn't use this quantity, we only used the norm of that quantity in the definition. And this is just the distance of gamma ti plus 1 from gamma ti. And guess what? So if you were mapping into any metric space, and then you had a metric on this, so if this is a metric space and there is a notion of distance of points, you would still be able to define this quantity via supremum of summation of length. And that emphasizes how basic this definition is and how little structure it requires on your target space so that you can make this definition meaningful. So the length of curves do have meaning for curves in any metric space, and they are really important objects in the study of metric spaces. So in my more advanced section where I focus on research level questions, I will soon also discuss why these two notions of length also coincide with the notion of one-dimensional Hausdorff measure. So that just brings everything together, but the Hausdorff measures themselves and also the reason why this equality holds requires a lot of background, which I cover in that section. So hopefully you enjoyed this video, and if you had never really stopped and thought about, wait, why two definitions of a curve, then I hope this will make things a bit clear. Thank you a lot for keeping your interest in my channel, and more videos on the way. Thanks a lot.